Now we will discuss the strengthening mechanism strain hardening. I will do that by some demonstrations. If you look at this little wire and we start to bend it, it becomes harder and harder to bend it after a while. And even if I want to bend it back, it's also relatively hard. I can do so. I guess you're aware of that you can break this wire by bending it a number of times. It becomes harder and harder each time. So, there it broke. You see? And what is happening in this wire when I do this is it becomes harder and harder during deformation. And we will look into what exactly is going on. We will go back to this picture about a dislocation line moving across some other dislocations. And as we are deforming the material, more and more dislocations start slipping into material in different directions, in different slip planes. And they are, of course, crossing each other. So the more the deformation goes on, the more interactions occur between dislocations in different directions. And after a while, they are hindering each other more and more, and the free areas where they can slip will be smaller and smaller, and the material gets harder and harder. And finally, the dislocations cannot move at all. They are actually stacked on each other, and the material breaks. Now we will discuss this out of a stress-strain diagram. Here we have the stress-strain diagram, and here we have the elastic part, and now we start deforming the material, and we move up the curve here. If we deload, we will go back and have a remaining deformation. Then if we load the material again, we will come up here and continue to do the deformation. But now we see here that we have increased the strength. The yield strength has increased from this position to that position due to the deformation hardening of the material. And we can continue to harden the material and deload again. And now next time we have a yield strength of this level. And so it goes on. But at a certain level, the material will break. And as you see here, if we have increased the strength from this level to this level by strain hardening, we have deformed the material from this point to that point, then we have a very, very little deformation space left here. We have lost a lot of the material's ductility. In the original material here, we had a very large ductility. We could deform the material from this point to that point before it broke. But if we have strain hardened the material, we made it strong by deformation, we are at this point. And if we want to load this material at this position, we go up here, get the yield strength here, but then we get the tensile strength, then the material breaks nearly immediately after the deformation. So, what we gain in strength, we lose in ductility. It's a very clear coupling between the ductility and the strength of the material. This can also be illustrated in this type of diagram, where we have the strengths on this axis and the deformation on this axis. And here we see curves for how the strength is increasing when the deformation is increasing. Here we have the yield strength, and here is the tensile strength. We can also see that the distance between the yield strength and the tensile strength is decreasing. They are going closer and closer to each other. But here they have also added a curve for the ductility. And you see that it goes down strongly. There is no scale for that one in this diagram, but roughly it goes from 20-25% in the undeformed material down to 1 or 2% when it's very strongly deformed to 80%. So it's a very clear trend that when you increase the strength by strain hardening, you lose the ductility. In the last diagram, we discussed only one material. Actually, it was a steel. But here we will see that there is a general trend that the ductility goes down when the strength increases. Here we have a diagram where we have plotted the properties for aluminium alloys in a diagram where we have the ductility on this axis and the yield strength on this axis. And each two-dimensional figure represents one aluminium alloy. And what is very clear here is that when we have high ductility, these alloys, we have a low yield strength. And when the ductility goes down, we see also that stronger and stronger materials. Strongest alloys we find here, they have the lowest ductility. Now we can also see that this is a logarithmic scale, so it's rather big differences. I mean, this goes from 50% down to a few percent when we increase the strength of the material. Now we can also realize that this is hardening by different hardening mechanisms. It's not only strain hardening. So anyway, we can realize that it's very clear that when we gain in strength, we lose in ductility. It seems to be a general trend. Of course, you can find some rather strong materials also with relatively high ductility. Another feature that has been pointed out in this diagram is that these alloys down here, they are as cast alloys. And all of these alloys are wrought alloys. And there we also see a trend, there is a difference. We can realize that the as cast alloys has generally a lower ductility than wrought alloys, especially if you compare them in the same strength region.